All right, so this will be part 2 of lesson 8.5, the integral test and the p-series, specifically focusing in on the p-series. Now, as you'll recall from the first half of this lesson, the integral test, we looked at each of these series in turn, and we already discovered that the one on the left is divergent. Again, it's divergent using the integral test, but it's also divergent because it's a known harmonic series, which we proved to be divergent earlier in the course. And 1 over n squared, we used the integral test to show that it was convergent. Now, a p-series is any series that appears just like these two. Specifically, the format for a p-series would be anything of the form 1 over n to the p, where p is a constant. Now, don't confuse this with a geometric series, where it's a constant raised to a variable. With a p-series, it's a variable raised to a constant. 1 over n squared is a p-series. 1 over 2 to the n is a geometric series. It's very common to mix up the rules for p-series and geometric series, or mix up the format for geometric and p-series. So being aware that that is a common mistake, be on the lookout. Don't mix up geometric series with p-series. Now, to generalize the p-series rule, we're going to treat this just like we did with the integral test. We're just going to take the integral, recognizing that the sum of the series is approximately the same as the integral of the function 1 over x to the p. So if I integrate this, I'm going to start by rewriting it using a limit. Limit as b approaches infinity of the integral from 1 to b of 1 over x to the p dx. 1 over x to the p could be rewritten as a power function, x to the negative p, allowing me to do a power rule. Add 1 to the exponent, negative p becomes negative p plus 1. Divide by that new exponent, negative p plus 1 is now in the denominator. Evaluating from 1 to b, following the fundamental theorem of calculus, plugging in b, plugging in 1, and subtracting, I get a statement that looks like this. Now, just looking at this, there's really not much I can do. I mean, I could rewrite it as a single fraction if I wanted to, but there's really not much I can do without knowing a little bit more information. Now, that information comes in 3 cases. This integral can be evaluated based on one of these 3 cases, and every possible case is going to fit into one of these 3 cases. Either 1 minus p is positive, 1 minus p is negative, or 1 minus p is 0. There are no other situations that are possible other than these 3 cases. So let's look at each of those cases in turn. Consider if 1 minus p is positive. Now note, if 1 minus p is positive, then that means that p is less than 1. In other words, if I just take the p value and add it over to the right side, add p, I would have 1 is greater than p, or p is less than 1. Just keep that in mind, that the statement 1 minus p is greater than 0 is the same as the statement p is less than 1. So if I look at that limit that I found a second ago, and if I recognize that 1 minus p, this guy right here, is a positive value, and consider if b goes to infinity, and that is always being raised to a positive exponent, this is just going to keep blowing up forever and always to infinity. Therefore, the series 1 over n to the p would diverge when p is less than 1. So p is less than 1 means divergent. On the other hand, if 1 minus p is less than 0, or p is greater than 1, that series, what's going to happen is this piece right here, 1 minus p, if this is always a negative value, because 1 minus p is less than 0, that means b to a negative exponent really means that's going to be moved downstairs. And as b approaches infinity, I end up having infinity on the bottom of the fraction, and if it's on the bottom of the fraction, that's just going to go to 0, leaving behind 1 over 1 minus p, which is just 1 over a negative number being subtracted. It's going to be some number. Don't know what number it is, but it's going to be a number, meaning that 1 over n to the p will converge when p is greater than 1. P greater than 1 means convergent. Case number 3, what if 1 minus p is 0? In other words, p equals 1. Good news, we've already done this one. That's called the harmonic series. 1 over n to the p, if p is 1 over n, which is the harmonic series, which is a divergent series. Therefore, we can generalize this into the p-series test. Given a p-series, which is of the form 1 over n to the p, If p is greater than 1, the series is convergent. If p is less than or equal to 1, the series is divergent. All right, here are some examples. Let's look at two at a time, starting with the first pair. Consider the first series, 1 over n to the 7th. We have a p series where p is equal to 7. 7 is greater than 1. Therefore, this is a convergent p series. Notice how easy that was. Yes, p series is another one of those super easy tests where you can just look at it, write down the answer. You're done. Divergence test, geometric series test, p series are examples of tests where you can just eyeball it and write down the answer. Be prepared for those three tests to show up over and over and over again, especially in the multiple choice portion of the AP exam. They like doing these three tests over and over and over again because they can just very quickly assess whether you know them by just eyeballing the answer. So if I look at the second one, 1 over the cube root of n, I have to recognize what that really says is 1 over n to the 1/3, where p is 1/3, which is less than 1. Therefore, that is a divergent p series. Here are two more for you to try. Pause the video here, hit play when you're ready. So looking at the first one, 3n to the negative 6/5, you have to recognize that it really says 3 over n to the 6/5. And even though there's a 3 in there, that 3 could be factored out to the front if you wanted to, and then it's really just 1 over n to the 6/5. So anytime you have a coefficient, don't concern yourself with it. Just imagine that it's not there and proceed. So 1 over n to the 6/5, p is 6 over 5, which is bigger than 1. Therefore, this is a convergent p series. Looking at the next one, this isn't a p series at all. This is geometric. 1 over 3 to the n, 3 to the n, that's not n cubed, that's 3 to the n. So because it's geometric in structure, we're not going to use the p series test, we're going to use the geometric series test. And I put that right on top of there for some reason. Okay, so I have 1/3 to the n. The common ratio is 1/3, which itself is less than 1. Therefore, this is a convergent geometric series, or convergent by the geometric series test. All right, here are two more, and then we're done. So take a stab at these, see what you can figure out. Go for it. Pause here, play when you're ready. All right, so clearly we're going to have to be using some serious exponent properties here to clean this up. So I recognize, looking at question E, I recognize that this can be simplified. Initially, I would rewrite it as n to the 2/3 on top and then 5n to the 3/4 on the bottom. I can continue to clean this up by subtracting the exponents, 2/3 minus 3/4, which should come out to be negative 1/12. The fact that it's negative really means that the exponent is going to land in the denominator. So the simplified version would be 1 over 5 times n to the 1/12. That 5 is a coefficient. You can just ignore it. It's not part of the problem. So what I have here is a p series where p is 1/12, which is less than 1. Therefore, we have a divergent p series. And finally, we saw something that looked similar to that numerator recently, n times the square root of n. Keep in mind, that's just n to the 3/2. And then on the bottom, I have n to the 4/3. Subtract the exponents, I get 1/6. Now notice I have a positive value, which actually means that this simplifies to n to the positive 1/6. It's not a negative exponent indicating put it on the bottom. It's a positive exponent, which indicates put it on the top. Technically, I have n to the 1/6 over 1, but I'm not going to waste time putting over 1. So if I look at this closely, this is not a p series. A p series is 1 over n to the p. This is not a p series, so what else could we do? If I see n to the 1/6, one test that I could always try is the divergence test. Take the limit as n approaches infinity. Infinity raised to the 1/6 is itself infinity, which is not 0. Therefore, this is divergent by the divergence test. But even though n to the 1/6 is not a p series, imagine if I rewrote it like this. Here's what I had before, here's what I have now. If I have n to the 1/6, that's the same thing as 1 over n to the negative 1/6, which is now structured as a p series, which means the p-value is negative 1/6, which is less than 1, which is divergent by the p-series test. So I can actually use the divergence test or the p-series test here to prove this one to be divergent. Just a little thing to think about as we are getting deeper and deeper into all the different tests, sometimes more than one test will work. It's your choice which test you want to use.